Greetings everyone, my name is João Damasceno. I will present this work entitled Exegetic Analysis of a Hybrid Solar Biomass Cogeneration Power Plant for a Poultry Industry Application. The authors of this work are me and the professors Edson Basso and Eduardo Burin. Here we have the outline of this presentation. We will have an introduction, the power plant description, the proposed schemes, thermodynamic analysis, the design condition results, the off-design condition results, conclusions, and references. First of all, I would like to start talking about the energy use. Energy is an important product to all humankind. According to the International Energy Agency, 81% of the world primary energy demand was supplied by non-renewable sources. Scarcity and environmental problems are related with this kind of energy. This brings to us the new energetic challenge. They are related to the better using of energy and the insertion of renewable sources. This brings to us, with this in mind, we have that multi-generation and hybrid systems can be used in order to achieve those challenges. So the objective of this work is realize a thermodynamic analysis of a hybrid Z biomass solar cogeneration power plant. So initially, a biomass power plant was proposed by Siqueira Neto. It is illustrated in the figure 1. This plant was designed to supply the electric and thermal demand of a real poultry industry located in Paraná. The plant used a biomass steam generator with a thermal efficiency of 86% to generate superheater steam at 520 Celsius degrees and 68 bar. The plant is able to ensure 12 megawatts of electricity and 16 tons by hour of saturated steam at that 10 bar, doing extraction in the condensation steam turbine. Two different schemes were proposed in this work in order to combine biomass and solar energy. So the first two of them is illustrated in the figure 2. It is a feed water heat scheme. Over 90% of the power plants in the world are using the feed water heat scheme. In this scheme, the solar field decided to heat the steam generator feed water to 180 Celsius degrees at design point. So for off design point, the solar mirrors were defocused to ensure that water temperature does not exceed 200 Celsius degrees for not affect the steam generator operation. The second one is a direct steam generation scheme. In this scheme, the solar field is coupled side by side with the steam generator in order to replace it by 50%. This scheme is illustrated in the figure 2. The solar field can be split in two sections, the evaporation section and the superheating section. The solar mirror under off-design conditions also are defocused in order to ensure the minimal load in the steam generator. Here we have the simplifying assumptions for our schemes. So steady state operation, negligible kinetic and potential energy changes, negligible pressure losses, negligible heat losses in pipes and heat exchange, but the heat losses in the solar field, dead state conditions. We applied mass, energy, and exergy balances to all components of our schemes. So initially on this screen, we show the linear Fresnel collector parameters. So for evaluate the energy entered in the solar field, we need take away the losses of the absorbed solar energy. So for do this in the feed water heater scheme, we use a model provided by the manufacturer. And in the DSG scheme, we also use a model but with a different model to the superheating section. Our schemes were simulated in two Brazilian cities in order to assess the region influence. Here we also have some annual performance indexes. So the first of them is about the biomass safe related with the scheme without solar energy, and the second one is the annual solar radiation absorption efficiency. So to perform the exergy evaluation, we consider it physical, chemical, and solar exergy. So this is the model for physical exergy. Here's the model for chemical exergy. It depends on the lower heating value for biomass and the coefficient beta. Beta depends on the component's max fraction of the biomass. Here we have the model for solar radiation exergy. It was proposed by Petella and depends on the environment and the apparent solar temperature. Here we show the first results. They are related to the design conditions. The biomass consumption was about 80 tons by hour in the base scheme. So in the DSG scheme, we can save 53 of the biomass consumption. In the feed water heat scheme, we can save 8.5% of the biomass. Here we also have the exergy results. The main destroyer of exergy is the steam generator. So when we couple the DSG scheme, we can decrease the exergy destruction in the steam generator for about 51%. And for combine the solar field in the feed water heating scheme, we can reduce the exergy destruction in the steam generator for about 9.8%, almost 10%. The overall exergy increase, but there is a lower destruction on the steam generator in the both of the solar field schemes. Some results for the off design conditions. Here we have some results of the design conditions. On the left side of the figure 3 we have the biomass economy. On the right side we have the solar field efficiency for the DSG scheme. The schemes were assessed in Palotina and Barreiras in a solar multiple range of 0.3 to 2.3. With a area on design condition, the fuel economy was of 5% for Palotina and 6% for Barreiras. So for Barreiras, even using a smaller area, it's possible to save more biomass because of the higher radiation levels on this city. Increasing the reflection area, it's possible to increase the biomass economy. However, the solar field efficiency decreased due to the necessity of the focusing to assure the minimal load in the steam generator. On this screen, we have the off-design results for the feed water heater scheme. So the annual fuel economy was smaller than the DSG scheme, with is slightly higher values for Barreiras. The solar field efficiency did not change more than 1.5%. Finally, in this work, a linear solar thermal system was coupled to a biomass cogeneration power plant, and the feed water heating scheme was coupled to preheat the feed water of the steam generator, and the DSG scheme was coupled to generate superheated steam. At design conditions for Palotina, the consumption decreased by 53% and 8.5% for DSG and feed water heater scheme respectively. The steam generator in the solar field are the bigger exergy destroyers. The best performance was attained in Barreiras due to the higher DNE level. Economy analysis must be realized in order to assure the best scheme. So here we have the reference, use it to do this work. And we are grateful to Human Research Program, PHNP, for supporting this research. Thank you all.